Okay, so as I mentioned in the previous part, we're going to deal now with a modification of the experiment in which we add an external force. So I was going to start already with the classification, but let's pause for a moment to understand actually what the modification is all about. Same thing as before still holds. We have that object, we have the initial displacement, velocity, we let the object to move according to the forces caused by the damping and the spring constant. But now on top of that, at any time t, we have an external force. And in this section, we're going to focus on what we call periodic forcing. That means a force which is periodic with some frequency given by omega. So, this right-hand side can be any force, right? I mean, any f of t, any non-homogeneous term can represent a force applied to the system. That's why actually it's called the forcing term. This non-homogeneous part of the equation in physical settings is called sometimes the forcing term. So in this case, we have a forcing term given by a periodic motion as a combination of cosine sine of omega t. So this now becomes a non-homogeneous problem, and we know already from the previous lectures that the solution will have two components, the homogeneous part and a particular solution. Now it's important to understand that the homogeneous part is what we just discussed in the previous part of the lecture. When we had that classification, overdamped, critically damped, underdamped, and so on, that was the part caused by the left-hand side equal to 0. So that now becomes the homogeneous part of the solution, namely the part of the solution that goes to 0. But now on top of that, we have the particular solution, which will be similar to the non-homogeneous term. So two components, two parts of the solution, the homogeneous and the particular solution, but the homogeneous, remember, is related to the characteristic roots which are negative. So now that component goes to 0. So if we look at the classification, we have very similar stuff like before. In the overdamped case, you have the homogeneous part, which is C1 e to the R1t plus C2 e to the R2t. Again, that's just one part of the solution. And then the particular solution, which will be similar to this. So maybe different coefficients, but the same omega. Again, pause for a moment and remember how we actually found this particular solution. Via the method of undetermined coefficients, we take a format similar to the right-hand side and we solve for the coefficients. So similar, but maybe different constants. So because of these features, and because of the fact that this goes to 0, right, the homogeneous part of the solution, this is called the transient solution. So the component of the solution that goes to 0. And because what's left is similar to f of t to the forcing term, this is called the forced response. Again, in engineering terms, if you want. This is because as t goes to infinity, eventually this approaches the particular solution, the so-called forced response, because the first part here eventually becomes negligible because it approaches 0. So if you want to sketch, basically, actually I'm going to do that after the critically damped case because that's very similar. So in the critically damped case, again, we're going to have the homogeneous part. So again, that happens when b squared minus 4mk is equal to 0. So in the critically damped case, we have y equals c1 e to the rt, the double real root, c2 t e to the rt, and again some combination of cosine sine of omega t. And so this one now is the transient that goes to 0. And the forced response. Oh, another name for the forced response is the steady state. The steady state, because again, this is what's left as t goes to infinity. The portion of the solution that is still there as t approaches infinity. So if you were to sketch these two cases, it'll look like this. For a while, the transient solution still has an influence. It goes to 0 and maybe some wiggle because of this periodic forcing term, but eventually it settles at a periodic motion. So for a while, in the beginning, in the first part of the motion, this is the effect of the transient solution. Again, with Maple, you will see much better what I'm talking about here, but that's the idea. And then as t goes to infinity, eventually it settles at a steady state. So eventually the only effect on the solution is from the particular solution. And then we have also the, what's next? We have the underdamped case. So the third case, underdamped. That's when b squared minus 4mk is, of course, less than 0. And in that case, of course, you have the homogeneous part as e to the alpha t, c1 cosine of beta t plus c2 sine of beta t, and again some combination of cosine sine of omega t. Once again, you will recognize immediately the part that goes to 0 because of the negative alpha. So that will be the transient solution. And what's left is the forced response. So in the long run, the system behaves like the particular solution. This is essentially in a nutshell, the main idea. Now, here comes the interesting part. What happens if you have no damping? So let's look at the fourth case, the undamped mass spring system, when b is equal to 0. And remember, in that case, the characteristic roots are r equals plus minus I square root of k over m. The frequency of motion is square root of k over m. Well, this is where the duplication part comes into play, if you look carefully. Why that's the case? Well, now if you look at the homogeneous part of the solution, there is no alpha, right? The main feature of the complex case with the undamped situation is when alpha is 0. So now your homogeneous part is just a combination of sine and cosine. But then these sine and cosines may duplicate the forcing term. So remember, if you have any duplication, if any component of the particular solution duplicates the homogeneous part, you need to put the extra t. Okay, so this is why you have essentially two sub-cases in the undamped case. Equal frequencies or different frequencies. So for example, case 1, let's call it 4.1, omega is not equal to root k over m. So distinct frequencies between the external force and the internal oscillations of the mass spring system. Well, in that case, you have a fully periodic motion. So if you write the solution, it'll be some combination of cosine root k over m t plus c2 sine root k over mt. And the forced response is just like before, some combination of cosine of omega t, sine of omega t. Fully periodic, and the amplitude of the oscillations is bounded. So this one will be bounded oscillations. Fully periodic. Bounded oscillations because you have a bunch of sine and cosines, and that's it, with constant coefficients. So remember, the cosine and sine can go up to 1 or minus 1, back and forth. And with some constant terms here, that means the oscillations doesn't go out of a certain maximum amplitude. So again, you will see with Maple much better, but the idea is that if you plot this, it'll basically look like that, you know, various amplitudes, but they don't go out of maximum and minimum amplitude. So fully periodic with bounded amplitudes, bounded oscillations, in other words. And then finally, like I said, the interesting case is when you have equal frequencies. So when you have omega equals square root of k over m, this is the so-called resonance. that's when you have the extra t, which will cause the amplitudes to go to infinity. In many applications, this is not something to be avoided, of course, because the system may break, right? I mean, if you have amplitudes that go out of bound as t goes on. So if these are equal, then you have duplication, and then in particular solution, you have the extra t. So your solution will look like this: C1 cosine of omega t plus C2 sine of omega t, and then the particular solution is t times some combination again, omega t sine of omega t. As t goes to infinity, this is what causes the amplitudes to go without bound. So this is what causes you or gives you unbounded oscillations. You should again immediately go over the Camtasia demonstration to see these cases in Maple. But if you want to put just a little brief picture on how the situation looks like, how the picture looks like, let's do it here. The idea is that it's going to go out of bound like that. I mean, the amplitudes grow without bound as t goes to infinity. Obviously, this is to be avoided. There are cases in examples in real life when a resonant system may cause accidents, like I forgot the name, but there is a famous bridge that became in resonance under the wind, or and so the amplitude, of course, went too far beyond the specification of that bridge, and then it broke. So one suspended bridge, something like that happened. So in the last part of the lecture, we're going to go over again some examples with solutions given to you, and then the question is to recognize again whether it's forced, unforced, whether it is in resonance or not, what type of motion, what's the transient solution, what is the steady state or the forced response, and so on. So stay tuned for the last part of this video lecture, but then again, make sure you go over the demonstration with Camtasia as well to see these examples.